In the earlier videos in this series, we took a look at how to define Boolean logic and the notation OCR will use in their exam, the various logic gates and their associated truth tables, and how to simplify expressions using Carnegie maps. We're about to embark on some tricky material, so it's highly recommended that you start by going back over these earlier videos to make sure the basics are fresh in your mind. In this video, we're going to take a look at the logic that is associated with D-type flip-flop circuits. A flip-flop is a very basic circuit which can store a single bit and flip it between 0 and 1 or vice versa. It has two inputs. The first is a control input, which you'll often see labelled as D. The second is a clock signal. The clock signal is itself provided by another basic circuit, which is responsible for constantly changing states from 1 to 0 and 0 to 1 at regular intervals or pulses like a heartbeat. The internal regular pulses or heartbeats are commonly needed in computer hardware. The CPU in your computer has an internal heartbeat or clock speed measured in hertz, which the control unit uses to manage the fetch, decode, execute cycle. In this situation, the clock or heartbeat is used to synchronise the changing of state of the flip-flop circuit. This will become clear in a moment once we work through an example. A D-type flip-flop circuit is what is known as a positive edge triggered flip-flop circuit. This means the output from a D-type flip-flop circuit can only be changed from 1 to 0 or 0 to 1 when the clock pulse is at a rising or positive edge. In other words, at the beginning of a clock cycle period, as shown here. If the clock is not at a rising or positive edge, then the output value is held and does not change. This circuit is fundamental to computing as it can be used as a memory cell to store the state of a single bit. This will all be a lot easier to understand if we work through a careful example. So let's see what we've got here. Here's the circuitry for our D-type flip-flop. You can see it's made up of several gates. Here's our two inputs, D and the clock signal, and here's our outputs, Q and not Q. Here's a description of what's going on, and here effectively is our timeline. So currently D is set to 0. The clock is currently set to 1. In other words, the clock pulse is on. It's at its rising edge. We're at the beginning of a clock cycle. And Q is currently 0. So here we are in the middle of our clock cycle. The clock pulse is currently on. We're not at the rising edge, however. The input D is still at 0, and the output Q is being held at 0. Here we are at the end of a clock cycle. Now the input D has changed to 1 as we can see here, but the clock is at a falling edge. Remember, we only change the state of Q if we're at the rising edge of a clock cycle. We're not. So although D is 1, Q remains fixed and locked at 0. Here we are, the clock is off. D is 1, but Q remains at 0. Now here, we're at the rising edge. The clock is set to 1. We're at the start of a new clock cycle. Because we're at the start of a new clock cycle, Q is able to take on the value of D. D is 1. And if you study the signal lines here and follow the logic of the AND gates, you can see how the value of D is now being taken on by Q. So because we're at the rising edge of a new clock cycle, the output Q can take on the value of D. Proceeding through, we can see here that the input D has dropped to 0, but we're not at the rising edge of a clock cycle, so Q is held or frozen at 1. Continuing to follow this simulation through, you will see that no matter what happens to the input value of D, The actual circuitry itself never allows the output Q to take on the value of D unless it occurs at the start of a clock cycle at a rising edge. Work through the video carefully now. Pause it if necessary. Check you understand what's going on in the explanation. Look at the signal lines in the circuitry and understand the output. So as you have seen from the example we just worked through, a D-type flip-flop circuit is made up of several logic gates and can be used to store a single bit of memory, either a 0 or a 1. You can therefore join multiple D-type flip-flops in sequence together in a similar way to joining together full adders in the last video. 16 D-type flip-flop circuits in sequence would be able to store 2 bytes, or 16 bits in memory. It's D-type flip-flop circuitry which is used in register memory inside your CPU and also in static RAM.